All right, folks, let's take a look at this example. Again, we've got a 12-foot long wooden sawn lumber joist. The joist is a 2x10. Again, you can take out the properties for a 2x10 out of any, resource that deals with lumber. For our text that's on page 644, tell you about the area, the moment of inertia, the section modulus, all those good things. But what we're trying to do is we're trying to find maximum shear stress on this 2x10 wood joist that spans 12 feet if it's got 200 pounds per foot of uniform load. So again, first thing I do is think about the shear stress formula. VQ over IB. All right? How are we going to get that V force, the maximum shear? Sounds like we better do a shear diagram. Okay? The first thing we need to do a shear diagram is we got to break or resolve this 200 pound per foot uniform load that stretches over 12 feet into a single result. How much should that resultant be? 2,400 pounds. And it acts right at the middle of the in the middle of the uniform load. All right? Now I'm not going to go through all the equilibrium equations because this is a pretty basic simple beam. All right? But you got 2,400 pounds acting down in the middle. I think everybody will be comfortable in me saying that the reactions on each side have to be 1,200 pounds apiece. If you don't believe that, go ahead and we'll, spend some time working the equilibrium equations, but that's going to be what it is. So, what does the shear diagram look like? Well, again, we just got done doing this a while ago, but basically it goes up to 1,200 pounds, and then what does it do? It what? Does it go straight over like this? Or does it slope down? Because every foot is going down 200 pounds. It's going down on a diagonal like this. Right? It goes down a total of 2,400 pounds. So if I'm up at 1,200, that means it goes down to negative 1,200. Where does it cross zero at? How far out does it cross zero at?
6 feet.
How did you know 6 feet?
It's 12 foot long.
Okay, so you said that just crosses in the middle. I mean, that's right in this case. You want to know mathematically how you do that?
Yeah.
It's the straight line formula. It's y is equal to mx plus b. But for our case, you just say, well, we're starting up here at 1,200. So this distance x, it's going to be 1,200 divided by the magnitude, or if you're doing math, the slope of the line, okay? And the slope of the line is 200 because it goes down 200 pounds every foot, all right? I mean, if you looked at the slope here, how far does it go down? 200 for every 1 foot, okay? If you're writing this in like the straight line formula, you'd say, where my slope actually in this case would be minus 200, okay? Y, I want to know where y hits zero at, and where do I start at? I start at 1,200, okay? So find me x. It actually becomes negative 1,200, negative 200 as you bring it on over, but that's neither here nor there. So 6 feet out, you're right. So anyway, the area here would be useful when I'm doing my moment diagram, but I don't need my moment diagram right now. So based on the shear diagram, the 1,200 pounds, my maximum shear, right? So stress is equal to 1,200 pounds. Hey, it's a 2x10 wood joist, right? You can go to your table on 644, and it says a 2x10 wood joist is really 1.5 inches wide by 9 1/4 deep. Okay? And again, the neutral axis is right in the middle. But that means the area outside the neutral axis is really half of 9 1/4. That's 4.625 times a half. What is that area? What's 1 1/2 times 4.625? 6.9 square inches. Now I'm going to have to multiply that by the distance to the neutral from the neutral axis to the centroid of that shape. How far away is that? Well, it's going to be half of 4.62, right? So I'll say 2.31. It's actually a little bit more than that, but we'll say that. What's my moment of inertia for this 2 by 10? Well, hey, you got a table there. You can see there that when you look at moment of inertia, it gives you a value of like 98.93. And the width of the beam, you already know, was 1.5 inches. Okay? So your shear stress, utilizing that formula, comes out to be what? $1,200 times 6.9 times 2.31 divided by 98.93 divided by 1.5. What does it come out to be? What is it? Yell it out when you got it. $128.9. The units would be pounds per square inch. Did you get 128.9? All right. All right. Let me show you something real here. Now this only works with rectangular shapes. So when you're dealing with like sawn lumber shapes. A shortcut to this formula only for rectangular shapes is this. 3/2 V over A. 3, the shear was 1,200. Divided by 2, and the area of this I can take out of my table is 13.88. Somebody calculate that for me real quick. Yeah, 129 again, right? So, I mean, it's the same thing. All right? Now, the reason why, and again, warning, you can only use this when you're dealing with rectangular shapes. Okay? The reason you can is that, you know, there's a certain relationship when you're using rectangular shapes. You got V, Q, you know, if you think about a rectangular shape as having a base and a height, think about what Q is. Q is base times height over 2 times height over 4. Okay? And I is 1/12 base height cubed, and the width, of course, is base. So if I run this out, I got V BH squared divided by 8 in the top, and then I got 1/12 B squared H cubed in the bottom, okay? And I can start, the base cancels with this. The height squared cancels with this and leaves h, okay? I can bring the 12 up top, and I got 12 ace, and I got v, and down at the bottom I got b times h, and b times h is the area. Okay, so 12 aces, 3 halves, so it works out, but only for rectangular